Hello and welcome back. Today we're going to be talking about an introduction to SolidWorks simulation and how we can use this tool to do some really cool things, solve some problems in the real world, and apply it to the problems we're going to be facing on the job and possibly in future classes. So computational modeling, what we're going to be talking about really through the length of this course is really a design tool. And you've had ME340, you've had the junior level design, you're probably looking forward to moving into the senior level design. And so what we're going to do is show you how you can use software to help improve the ideas that you come up with. And once you have those ideas in a solid model or in some simulation package, how to iterate on that to actually make those even better. You can do that without actually having to make a physical prototype. So with computational modeling, you can design better parts, better assemblies, and better products. And how do we do this? Well, the underlying principle here is that once we have a digital model of our part, we can analyze that digital model, make quick changes to it, reanalyze it, and do this in our design cycle to keep improving without costing as much money as it would to actually physically prototype it, then run tests on it, analyze those tests, and whatnot. And what the computational packages allow us to do now is not only do this with individual parts, but we can do this with assembly. So we can put together a whole device, a working device, at least within the confines of the simulation environment, and then model how this thing's going to perform when it's used by actual people or is put into its working environment. And in this way, we can improve our production cycle, get better products out to market. So they say you can model just about anything with SolidWorks, and that is largely true. If you Google SolidWorks designs, a whole bunch of things will come back. One image you'll find is this sort of four quadrant at the top where we've got a motorcycle, we've got a small prototype car, we've got an airplane fuselage. On the bottom right, we've got a small bike, maybe something like you'd see designed in ME340, or more likely the senior design ME440. But each of these things consists of individual parts. These parts are put together in assemblies, and these assemblies can have some degree of functionality, so things can move around, they can twist, they can move, so you can see how parts may interact with each other, clearances, tolerances, fits, how those might affect things as well. But what largely people may not know about is that SolidWorks can also do analyses, and those analyses allow us to apply the laws of physics onto our model to see how that model is actually going to perform. And we can have it perform in a specific environment where we know all of our boundary conditions, so our loads, our temperatures, and whatnot, or we can subject it to a range of environments and figure out what's going on there. The bottom two figures are showing you something just like that. The bottom left figure shows some results from simulations done by Dr. Ruben Kraft and his team, where they are looking at how the human spine, that sort of red thing right in the middle of the body, reacts when you are subjected to an ejection from a seat in, I believe it's an airplane environment. So what they're trying to figure out is what actually happens to the body in this dynamic event, right? What sort of loads are imparted to the body and how those loads change with the design of the contours of that seat itself. So it's some really cool stuff that involves biomechanics, biomaterials. It's not a linear problem at all. It's not a static problem. It's time dependent. So it's fairly complex, but that's sort of what their research is into. On the bottom right, I'm showing you some results from research that I do. And here we're showing this is a magnetically actuated tube. So that blue thing you see is a cylindrical tube. In the middle of it is essentially a chute that runs from bottom to top that's driven by electromagnetic fields, and it actually pushes that piston forward, so it pushes a fluid forward, and that chute deforms. And once it deforms, you can actually push fluid in what's called a peristaltic mechanism. So it's made to try and reduce the amount of damage that blood or some biological fluid will see as it's being pushed along forward. So not only can we do the deformation of the material itself, that material is deformed by freely varying electromagnetic fields, and those fields are moving. Plus, they're interacting with the fluid, so we've got fluid back pressures as well. So it's a really complex problem. This one isn't necessarily in SolidWorks. It's done with COMSOL, but SolidWorks has the functionality to do most of this, to couple fluid problems, solid problems, and I'm not sure about the electromagnetics bit, but you can do that with a force or a load boundary condition as well. And if you have any interest in magnetically actuated large deforming structures or origami engineering, we're mapping this into some 3D printing technologies as well, please reach out to me because we're always looking for undergrads to work in the lab. And so when we say you can design just about anything in SolidWorks, and yes, that's true, in general, using finite element analysis, you can analyze, you can design just about anything. And to give an example of that, on the bottom left here, I'll show some results of some work that's coming out of my lab, where folks have built this experimental structure on the bottom left, and it consists of a thin piece of rubber on the very bottom. That's that clear thing you might see. The whole thing's sitting on a table, and those patches are rubber that is filled with a magnetic material, which is kind of cool. And what that does is when it's subjected to a magnetic field, as we're going to see here in a second, the magnetic field oscillates. It goes up, it goes down, it goes up and goes down, reverses direction, and those patches respond to that magnetic field, and they try and turn into the direction of the magnetic field, which gives you this sort of accordion motion back and forth here. And as we cycle the field to either larger strengths or smaller strengths, the degree of that cycling gets either bigger or smaller. So pretty cool stuff, yeah? Well, on the right, what you're seeing are finite element simulations of probably several dozen prototypes of that device when it's subjected to an electric field, right? So each of those data points, each of those points on that graph is a prototype of a different size, a different shape, different strength magnets that are attached to our little piece of rubber, different thicknesses of those magnets, different stiffnesses of that substrate, different thicknesses of that substrate, so all different design parameters that we've built into this. And what we do with our analysis is we look at it for shape error. How close does it get to the target shape, that accordion structure that we want, and how much does it cost? We can plot this on a graph, and what this allows us to do is get a really good understanding of what's called our design space. All of these simulations tell us how well this thing does with respect to shape. You want that smallest, so you want the smallest shape error, or how it does with respect to cost. You want the lowest cost. So we want to be in that bottom left corner, which are the ones we've highlighted there. This would have been impossible to do experimentally. Those small magnetic patches are made with something called barium hexaferrite, which is really, really expensive. It's about $1,000 a kilogram. That underlying substrate for the silicone elastomer, not really expensive, but it's a pain to make. It takes about a day or two to cure, and so this would be a long time and financially expensive endeavor. But here with simulations, we can knock all these out in about a week. So as I said, we use this simulation to run through numerous numbers of prototypes so that we can see how they perform, such that we can pick the one that performs the best for us in our particular application. That's traditionally how this prototyping has been used, to test a product to see if it works, but we want to get away from the prototyping because it's expensive and it's time consuming. You may remember from ME340, if they're still talking about the example for EXO and how they've developed their ergonomic kitchen utensils. Here's an example. You may have seen about the evolution of their potato peeler. So from right to left, we've got the standard way these things have been designed for probably a century. And then just to the left of that one, you've got the potato peeler head with a nice solid shaft that's a cylinder. The one next to that, the cylinder's got some contours, then it has some cutouts, then it's got different cutouts, different contours, and eventually they moved to the one on the far left, which is the product that they ended up marketing. Yeah, and you may look at this and think, okay, 6, 7 prototypes, not so bad, but what you don't see is the hundreds of physical models that they actually built of this thing before they actually went on to put the final one into production. Now, imagine if you could simulate these things in some sort of finite element or CAD model, and then have that model do all the analysis that you would do physically. That's really the ultimate goal of CAD, computer-aided design and analysis. Can we actually simulate everything that we want to know about a thing in the computer? And that's the way this field is moving. There's some people who do that sort of research here at Penn State. I'm not necessarily one of them, although I do teach the design side, but I don't do research in design. But that's really where they're pushing everything to go. So simulations enable us to validate designs virtually. So what does that mean? Well, the validation process means that on the computer, We run the simulation through whatever analysis we're going to run it through, and then we see how well it performs, and we test that performance versus our expectations. And so we do this before we actually commit resources to creating a prototype. I've said before, the future of this stuff is, can we recreate what the user experience is for a device, or what it's going to perform like in its environment? And that's moving into the realms of virtual reality if you're really going to be on the cutting edge of these things. And as I said, there's some folks in design here at Penn State who are doing that level of research. My particular foray into this is on the bottom right, in that sort of accordion shape, subject to a magnetic field that I was showing you before. We had tried for a long time to get one of these things to actually do something useful for us. If you saw the one there, it just sort of stayed in place. Well, we had some students do simulations. They worked out this thing is sort of a friction-based walker. Can it pull and push itself and shift its weight adequately? Does it bend in the right directions? Do the magnetic fields act on it enough? We simulated these things, and then once one of our simulations started to show some promise, that's the one we actually made. And we made that one because we don't want to make hundreds of these things because the materials are expensive, time-consuming to create, but our results were pretty good. Now it's subject to this oscillating magnetic field. It goes back and forth, up and down, and as you can see, it actually walks forward while it's in this field. It looks kind of cool, looks kind of creepy, but it worked. And it worked because we figured out through simulations how to actually distribute the weight, distribute the loads, where to put the patches to make the thing do what we wanted it to do. Well, when we validate designs virtually, what we're going for here is to improve the product design, to reduce the number of prototypes you have to make, and most importantly, to have a shorter and less costly design cycle. So on the left, you may have seen figures like this from your junior design class, where the engineering design process here is sort of highlighted and visualized for you. We always start with sort of asking questions. What's the product we need to make? What's the problem we're trying to solve? Then we imagine solutions. We come up with a plan. We try and create solutions based on that plan. We run experiments and we see how the thing works, and then we try and improve it. And that bottom left quadrant, right, along around 7 o'clock, the experiment and improving, that's where the virtual prototyping comes in. Can we run our experiments virtually? Can we generate how well it works or doesn't work? Can we improve it virtually? And can we then run new experiments on that improved version, all done virtually? So we can get through this product cycle several times over before actually having to make the prototype at all. So within SolidWorks simulation, or really any other package that you deal with, there'll be some basic types of steps that you have to take. Right? The first one is defining the geometry. We have some way to come up with our CAD model. Once we have this CAD model, we can assign material properties to it. What's it made out of? Those material properties then are really tied to the types of analyses we're going to do. If we're just going to look at a structural material, then, and it's a static material, meaning we don't deal with time dependence, really all we're going to need is some sort of modulus, especially if we're just looking at it in a small deformation or linear range. If we're going to take this thing to failure, we want to know when it fails and what it looks like when it fails, then maybe we have to introduce a yield stress so that we can sort of mark off when that happens. If we're doing something that's time dependent, then we're going to need viscoelastic properties or viscous properties. Like, how does this thing flow over time? Does the rate of loading impact how fast it deforms? Does it any sort of stress hardening or strain hardening? So those things can all be built in. We're going to start off in this class dealing with linear materials, basic Hooke's law stuff, but then we're going to sort of add on layers of complexity, because really it's those layers of complexity that the finite element method really does well with, because it takes that complexity really out of our hands. We just tell the model, here's how it behaves, and then you go off and predict all the complex stuff for me. So after we've defined our geometry and assigned our material properties, then we do what's called creating a study. And this study is kind of a misnomer. It's not a verb, it's a noun. We're actually going to create a study where that study tells the software, here are the physics that you're going to use, here are the governing equations you're going to apply, and here's the solution method you're going to use. Once we know those things, the software goes off, it does its thing, and then it gives us back a solution. Yeah. Well, actually, let me say there's one more step in there after we've created our study. We have to define the operating environment. In the mathematical nomenclature, they will call this boundary values or boundary value problems or boundary conditions. Essentially, for imagine a statics problem, we need all the components of a free body diagram almost. Right? What loads are acting on it? Are there any points that are constrained such that they can't move? And things like that. If it's a thermal problem, we need to know, is it subject to convection? Is it subject to conduction? What are the temperatures that are prescribed in any given location? Or is there any heat flux prescribed in any given location? All these things about how it's going to engage its physical environment. And then finally, the processing and reviewing of results. So the processing is, can we generate the solution for this? And can we take that solution and then turn it into some form of data that we can actually deal with? Largely, people, when they report on finite element methods, they give you pretty pictures, which have either a stress distribution or a strain distribution, or to tell you something about the von Mises stress. And so those are the things that people take away from the simulation to help them answer their question. So one thing to remember about finite element methods is that they'll almost always give you numbers if you set the problem up correctly. The issue is whether those numbers are actually meaningful to you, and the best way to figure that out is to ask yourself, do the numbers that I have requested from this program lead me to a solution of whatever questions I wanted to answer, right? So let's say, for example, you wanted to know whether or not a part would fail under a given load. Now, do the results give you some measure of that yield stress so that you can, a measure of say, the von Mises stress compared to yield, so you can actually make that comparison. If you can't, then maybe you need to go back to basics on your simulation and figure that out. You just have to make sure that the questions you're asking of your model can be answered by the model that you have built. And it's pretty much like that really with any software. The user has to define what they want because the software is only going to do what you tell it to do. Kind of goes without saying, since we're going to be using SOLIDWORKS, that the geometry for these parts has to be modeled in SOLIDWORKS. It's the quickest and easiest way to do it because SOLIDWORKS then will have native to it all of the features and components of that model. Yeah, you can use some other sort of pre-processing software and some other CAD software. You can export to an IGES or some other type of format and then import that back into SOLIDWORKS, but those, you're always going to find that there's going to be something wrong, especially if you're doing a complex model that either has small features or small tolerances or assemblies. So for this class, we're going to say, model the software, the geometry in SOLIDWORKS, and then we can do the analysis in SOLIDWORKS. And that's actually something that sometimes some professors don't know about. SOLIDWORKS actually has a good suite of analysis packages. And other folks use Abacus or ANSYS or Nastran. I myself use COMSOL, Multiphysics. But again, SOLIDWORKS has this stuff built in, and largely we stick with SOLIDWORKS for this class and for this sequence because you're already learning SOLIDWORKS in previous classes. You're going to be adept at making the geometries, so why not use the package that can actually do the analysis for you? And SOLIDWORKS does a good bit of analysis, a good bit of wide range of different topics in physics that it can apply. So it's good in that sort of all-around solution methods and all-around sort of package to solve problems that you might be able to throw at it. And of course, each of the different software packages has their particular niche. COMSOL will do some sort of weird electromagnetics things that SOLIDWORKS may not be able to do, or Abacus can maybe take on some strange material behaviors that something like SOLIDWORKS couldn't do. But for general use, SOLIDWORKS is a good place to start, good place to learn, and you can get up and going pretty quickly. So that next step about assigning material properties, what you're trying to do here is provide a little bit more definition about the part or the structure to be analyzed, and really, what is it made of? Now, for a basic structural problem, you can imagine we've got our stress strain curve here, bottom left, we've got this straight rise over run for Young's modulus. We're going to define possibly a yield if it's an important thing. Then if we get into the nonlinear behavior, what happens post-yield? You've got your plateau, you've got strain hardening, you've got necking, you've got fracture. And so different types of models may incorporate all of these different regions of our stress strain curve. Why? Because if you want to know what happens to something, while it's failing, right? Imagine a crash test or an impact test for a car. They're running these things from the car is perfectly fine, the car is moving along, then it impacts something, and it's going to go straight through that linear region, straight through yield, possibly into the strain hardening, and then up to the ultimate strength. So we need to know what happens over the whole range. You can consider similar things with thermal properties. If the properties change with respect to temperature, or they change with respect to the rate of change of temperature, then those are things that we can build into our material model. But we'll start with the linear stuff first, and then we'll add in that complexity as we go along. So the next step, defining what type of study we're going to use. Again, that's that sort of basic physics that it's going to apply. And SolidWorks has built into it lots of different classes of these basic physics already. So you've got linear static behavior, you've got nonlinear behavior. There's things for material, composite materials, or frequency responses, cyclic responses, as well as the thermal and the fluids and whatnot. So the type of study we create has to be matched to the physics, and then it applies the correct governing equations. We'll request from us the right material properties that are involved in that physics, and we have to provide it with the right environmental conditions. So just to sort of touch on the math here, just because I like the math, these environmental conditions, really, they're just boundary values, right? Consider that, and don't forget, all of this stuff is just trying to solve the underlying differential equations that govern this system. And all differential equations have boundary conditions or some sort of starting values. So whenever we set up a problem, we have to have an understanding of what all those are going to be, because we have to define them going into the problem, or else the solution procedure is not going to work. Okay, so our operating environment, continuing on with this idea of doing structural problems or static problems, how will the product be held and what forces are acting on it? Here, showing you a bracket for hanging up a picture. You can imagine this thing's nailed into a wall, but yeah, what type of wall is it nailed into? If you've ever hung a picture, it's going to behave differently when you attach it to a wall. If you get into a stud, or if you get it into drywall, or if you got a wood paneled wall, all of these different things affect that type of boundary condition that nail's going into, but then the bracket itself is pressed against something. And what it's pressed against might have some elasticity to it. It might have some give to it. You can also imagine that whatever it's attached to, it can push against it, but the thing it's attached to, the wall, can't pull it. So it can move away from the wall freely, but it can't move into the wall freely. It actually has to deform the wall. So all of this stuff has to be taken into account, even in addition to the fact that, yeah, somewhere on here, you've got either a wire or the frame for the picture that's going to be pulling it down. So where's that located? What's the direction of that load? All of these things have to be taken into account in our model. And the closer we can get to something that is, what do they call it? Statically equivalent to the real case, the better we're going to be for our solution. We got to get close to what's actually going on in a static sense for this thing to be realistic. So this next processing step really is the meat of the matter. This is where we actually solve the problem. Given the information we have about the model, we're trying to figure out how it responds. So every time you hit that solve button or run or go button on a software finite element package, just don't forget that what it's doing behind the scenes is breaking the model into a mesh. A mesh just means that it's discretizing or breaking up the solid geometry into lots of smaller pieces. And then within each of those pieces, it's applying the relevant laws of physics to generate a system of equations. And then it's trying to solve that system of equations simultaneously over all the laws of physics that we've told it to apply for this particular study across the entire volume of the whole part, all at the same time. Now, it uses linear algebra to do this, but that's what it's doing every time. And if it can find a solution to that problem, then it returns the results to us. Now, what's even cooler, if you step back and think about it, is that there's a couple 100-year history in the sequence of technological development that have brought us to the point of being able to do this for, like I said, just about any problem. There's a couple 100-year history of solid mechanics, meaning, how do we take mathematics of calculus, apply it to the motion of an individual part or individual point or range of points within a solid body. If we deform that body, where do all the points move? If those points are moving relative to each other, that means the thing is straining. So how do those strains develop? How do those turn into stresses? So there's a lot of research into material science that's gone into this. And now, once we know that things are being stressed as it's deforming, that stress necessarily brings up questions of, well, is the part actually going to fail? What's going to happen there? So how do we then analyze that? Well, we take these equations, we break this thing down into small individual chunks, and then we use the mathematics of finite element methods to turn all of those equations that predict our stresses into a cohesive problem that a computer can solve. And that required a few decades of actual computer science to evolve basic solution methods now into more complex solution methods that work much more quickly. We've gone from being able to run these things only on punch card driven computers, then to desktop PCs, now small clusters and mainframes that even you and I have access to. So that's actually some really cool stuff, and it's taken decades to get here, but that's where we're at. So lastly, our step here, reviewing the results. Once we actually have our results, what we're trying to do then is see, is the thing ready? Are there any changes we could make to improve it? Can we do these within the software, make some more predictions to see if that gets us closer to some target response or target behavior that we want? As always, we want a better outcome. Can we make a higher quality part? Can we make the thing do what we want it to do better than what it's doing? Can we shave weight? Can we add strength? Can we make it more ergonomic for the user? All of these things are things we're trying to answer, and we want to see if we can then move on to the next phase, which is usually a physical prototyping with more confidence. Are we more sure that it's going to work? And if we go back to our left-hand figure of this engineering design process, we're really just trying to iterate around that cycle as quickly and as cheaply as possible. So to sum it all up, SolidWorks is a tool. What we're trying to do is, use this tool to analyze real-world problems, and so we have to match our analysis type to that problem. We try and recreate the real environment using boundary conditions that represent the problem adequately enough. Then we generate results, and we use those results to see if they answer the questions that we need. Do they tell us what we need to know to make improvements to our part or our product? When do we do this? Well, we're doing it at a point early on where we're trying to save time and money in the early phases with prototyping. Later on, we may want to investigate some complex phenomena and well-developed problems, sort of like that walker I told you about. We'd been making the things for a while. We couldn't get them to walk, and so we decided, okay, let's actually do some analysis. Then we actually got them to walk, and then once we got them to walk with that analysis, we now analyzed them further, use some higher-level physics. This is more electromagnetic stuff, but use some higher-level physics to investigate what's actually going on in the individual patches, and is there something that we thought was happening that wasn't happening? And it actually turned out there were a few things that we assumed that weren't actually true, and we only found that out through simulations. And then finally, can we use these simulations if we're confident enough in them to explore or search for unknown relationships? And what's cool there is if you go back to this idea or that design space that I showed you, where we got dozens and dozens of points that tell us how this thing performs with different parameter settings in our model, but maybe there are relationships in there that exist that we can't see. And so when AI and machine learning are coming online and getting integrated with these design tools that help us learn about the system we're staring at, even if we can't see some trends, maybe those software can. And again, it's a cool area of research, not necessarily mine, but I'm working with some people who do that, and it really is going to be the future. When we have machine learning and AI able to do the iterative design for us and push us more quickly to optimal designs than a human user could, because they can actually see and understand more of the interrelationships in the data that we can. Well, thank you for watching this lecture on SolidWorks and the introduction to modeling and simulation using SolidWorks. Hopefully you've learned about the background of SolidWorks, what's going on behind the scenes, a little bit of the history of how we've gotten technologically to this point, and when and where and how to use these sort of computational tools. Next lecture, what I want you to look out for in the video is we're going to be talking about the different types of SolidWorks packages that there are, and then the one after that, how to access those packages and start doing this stuff online for yourself. All right, thank you again, take care, and we'll see you next time.
you.